Why can an EC motor run cooler and potentially last longer? The useful answer is not EC is always cool. At the same shaft demand, a permanent magnet rotor can avoid induction rotor current loss, while electronic commutation controls the stator current. But total temperature still depends on every loss and every thermal boundary. Lock the comparison first: same shaft power or torque, same speed, airflow over the motor, ambient temperature, duty cycle, mounting, enclosure and measurement method. A cooler surface photo from a different load does not prove lower winding temperature. Map the losses. Electrical input becomes shaft output plus stator copper loss, iron loss, rotor loss, electronic switching and conduction loss, bearing and aerodynamic loss. In an induction motor, rotor current produces rotor loss. A permanent magnet rotor changes that path, but it does not eliminate stator, iron, electronic or mechanical heating. This Longwell cutaway shows an ECM product family architecture: electronic control unit, permanent magnet rotor, sealed structure, and bearing system. It is physical evidence of construction, not a universal efficiency, temperature, or lifetime result. Heat must travel from winding and electronics through internal interfaces, housing, and moving air to ambient. Thermal resistance at one interface can dominate. Dust, restricted airflow, a hot enclosure, poor mounting contact or recirculated air can make an efficient motor run hot. Part load operation matters. Electronic commutation and speed control can reduce input when the application needs less output, but switching strategy and airflow over an air-over motor also change with speed. Evaluate the complete load speed cycle, not only rated operation. The installed blower image shows a real motor attached to a crossflow assembly. It does not prove why the system is hot or cool. Fan load, blocked inlet, wheel friction, bearing condition, supply quality and control command can all move the motor operating point. Runs cooler must name the temperature. Housing temperature, winding average by resistance, embedded detector, bearing temperature and electronics hotspot are different measurements. Use the method required by the product standard and acceptance plan, then wait for defined thermal equilibrium. Temperature is one reliability stress, but not the only one. Insulation aging, bearing lubricant, electronic capacitors, solder joints, vibration, moisture, contamination, voltage transients and start-stop cycles all contribute. Lower temperature can improve margin, it cannot guarantee a specific service life without validated design and field data. Protection should act on the actual risk. Define thermal sensors, current limit, locked rotor response, derating, alarm, shutdown, restart and communication behavior. A controller that reduces torque or speed may protect the motor while the process loses airflow, so the system also needs process supervision. Test under equal conditions. Record ambient and inlet air temperature, shaft demand, speed, voltage, current, input power, airflow over the motor and temperature at defined points until equilibrium. Repeat across the real duty cycle and worst credible environment. Qualified personnel should follow the exact product and electrical instructions. For a thermal and reliability review, send the exact motor and fan model, shaft duty, speed range, ambient and airflow envelope, enclosure and mounting, load cycle, power quality, control mode, temperature limits and method, protection logic, bearing and electronics requirements, contamination, service access and lifetime target. That evidence tells you whether an EC solution truly has more thermal margin. For a project-specific EC motor thermal review, contact Longwell.